afternoon. My name is Ryan Park. This is Nayang Yang and this is Angela Yang, and we're going to be presenting our project entitled Biofeedback for Correction of Dance Moves. Our project mentors were Dr. Sylvia Kokelj and Professor Predrag Spasojevic. In our presentation, we're going to be going over the background and introduction, the procedure, results, and conclusions.
This project mainly dealt with different types of dance injuries that ballet dancers could inflict upon themselves through practice. So ballet is very concentrated on the different forces and balances while they're doing twists, spins, and jumps. But there are a few different injuries that correlate to different movements. In this trial and this experiment, we studied the Arabesque turn. Two injuries that are mainly associated with it are either hip compressions or stress fractures in the spine, from when the dancer lifts his or her leg up incorrectly using the wrong muscles.
As Nayang said, we focus mainly on the Arabesque turn. This is when the legs are held perpendicular, like this, and the dancer turns a full 360 degrees on the standing leg. A common problem in this movement is called drooping leg syndrome, where the lifted leg falls a bit. This is due mainly to two reasons. One of them is gravity. The leg comprises about 15% of the total body weight, so the hip joint needs to exert a substantial force to keep it up. Another reason is conservation of angular momentum. Because the leg is extended so far from the body, the turn tends to be rather slow, and sometimes the dancer will lower their leg to speed up the turn. This usually manifests itself in an oscillation where when the leg is visible to the audience, it's kept perpendicular, but when it's not visible to the audience, it falls a bit. To study this phenomenon, we had to learn different ways to express three-dimensional rotation. One of them is called Euler angles. These are rotations around the x, y, and z axes. A roll is like this around the x. Around the y is called the pitch, and then around z is called yaw. These are rather easy to understand, but they are rather imprecise. For example, the order in which you express these is important. If you say x, y, and z angles, but it's different if you express them in a different order but have the same angles. Additionally, there's a problem called gimbal lock, where say you rotate the z-axis 90 degrees so that it goes up to the position where the y is. In that case, it's confusing whether you should rename the axis or not for the next rotation. Another way of expressing three-dimensional rotation is through quaternions. These are more complicated because they involve complex and imaginary numbers, but they are more exact and don't have problems like gimbal lock.
In our project, we try to study drooping leg syndrome, which occurs in ballet dancers practicing the Arabesque turn when their leg doesn't maintain 90 degrees. In order to combat this problem, we attempted to create a computer program or application that could be used as a teaching or practice aid, and we hope that it would give feedback to the dancers whenever their leg drooped below 90 degrees, and hope that it would reduce chance for injury.
So throughout this project, we used two different sensors from two different companies. The first one was from Yost Engineering Incorporated, or YAE, and our second one was from InventSense. There are a few differences between these two sensors. One is that the YAE sensor connects to a PC using a wireless dongle. Meanwhile, the InventSense connects to an Android phone through Bluetooth. The second is that the YAE sensor only allows us to record data in quaternion numbers. Meanwhile, InventSense gives us a wide variety of different recording data. For this experiment, we decided to use quaternion numbers and Euler angles. The third problem or difference is that the YAE sensor has a tear button on the interface of the PC, where whatever direction that we're holding the sensor, if we click tear, it will orient itself to that axis. Meanwhile, the InventSense, there is no such application on the Android. Therefore, we just had to assume that it was being oriented to the Earth's magnetic forces. So in order to find out how the InventSense recorded its data, we did 4 predetermined steps, graphed the data, and decided to interpret these for our later experiment. The first step, as in step 1, you could see the dancer is just standing still for 10 seconds. In step 2, the dancer extends her leg 90 degrees in front of her, then sets it back down. In step 3, the leg is abducted to 90 degrees to her right. And finally, in step 4, the dancer first extends her leg up 90 degrees, then brings it around 90 degrees to her right, and then sets it back down. There are 2 things to notice in each of these graphs. One is that for roll and pitch, which are red and blue, those numbers always start from the same. For instance, roll always starts from 0 degrees and pitch starts from 100. Meanwhile, the yaw tends to drift and starts from a different number each time. We believe that this came from a glitch in the gyroscope, the drift, and that was embedded in the InventSense beforehand. The second problem could be seen in step 2. There is an Euler glitch labeled in the graph. This most likely came from when the dancer extended her leg 90 degrees in front of her. It caused a gimbal lock, as we explained before, where the axes were reoriented 90 degrees, causing the spike in the data. Finally, when we did the data logging, we used both sensors on the dancer, so we got all the information that we can. On the top is the yay sensor, and this is a photo of how it looked like on the PC when we were logging data. The bottom is the InventSense, and coming up is a photo of how the application looked like on the Android.
These are 2 samples of the data we took from the sensors. On the top is from the InventSense. The first line is quaternions, the second line is Euler angles. And on the bottom is a sample from the yay sensor, which is in a modified form of quaternions. We had to extract only the values, the numbers that we got, using a MATLAB code, and we had to get rid of extraneous characters such as the commas between values so they wouldn't interfere with our data analysis.
As part of our program, we created a 2D animation program by modifying a pre-existing program called Learning to Understand Euler Angles. This previous program, as you can see, had an interface where the user could input their designated Euler angles. And however, the program would only display the Euler angles as static pictures. So we had to customize it so that we would remove the interface and make the animation program display the Euler angles as an animation. It would animate any data file that we selected. For our final program, we decided to use MATLAB rather than Python, which we were debating on, because we found that it was a lot more effective for our purposes. For the data that we used, we only used the InventSense data because it returned values in Euler angles. We attempted to peel quaternions and convert them to Euler angles, but due to time constraints, we realized that it was a lot better and more efficient to use Euler angles, and we only isolated the pitch values.
Now we're going to watch a video of our volunteer dancer from GSET who did our trials for us. As we said before, the dancer did have both sensors strapped to her leg. However, we only used the data from the InventSense, the Euler angles. And as we watch this video, I'm going to mention 2 things that are important and that will come up later in the results. The first is that the dancer takes a step forward before swinging her leg up to complete the Arabesque turn, as you can see above. The second is that the dancer did not dance or complete the trials in the best situation. First of all, instead of point shoes, she's wearing socks. And second of all, dancers are more accustomed to hardwood floors, and we made her dance on the tile floors outside in the elevator.
These are the results from the trial that you just saw. The red line represents the roll, the blue line represents pitch, and the green represents yaw. The first thing you might notice is that the x values remain constant along the entire time. This is a sign of good technique because for the leg to roll around the x-axis, we need to twist the leg, and during an Arabesque turn, it should be kept as straight as possible. Next is the pitch, the blue line. This is how much the leg was lifted. So because the leg is perpendicular, you would expect that the amplitude of that large peak is around 90 degrees. It's actually around 110 or 120, and this is due to, as Nayang pointed out, the step that she took before she did the turn. This threw off our calculations a little bit, but once we accounted for that step, we found that the leg actually was lifted around 90 degrees. Finally, there's the yaw, which goes down and back up. This is the movement of the leg around the body, this way. So since the dancer rotated about 360 degrees, it should register a 360-degree turn. The reason it doesn't go downwards a full 360 degrees is because the InventSense sensor can only log plus or minus 180 degrees. So to represent that full turn, it had to go downwards, then back up. This is the final product after we modified the code. This is our final product after we modified the Understanding Euler-Ingles code. These planes that you see represent the data you just saw in the graph. The red, blue, and green planes correspond to the red, blue, and green lines you saw. The circles represent rotational planes that the Euler-Ingles designate. They are built like one on top of the other. So first the red plane is built, then the blue is built with respect to the red, then finally green with respect to the blue. Just like in the graph before, the red plane stays pretty much constant. Meanwhile, the green seems to be moving the most because it is built with respect to the blue, so any movement or change in the blue plane also is reflected in the green plane.
Now we'll talk about the program that we finally created. At first we tried to create a program that could in real time give feedback to the dancer, but again due to time constraints we found this really difficult and we had to use another alternative way which nevertheless worked. So originally the dancer puts on the InventSend sensor and performs the Arabesque turn, and the sensor logs the data onto a data file or text file, as you can see. The data is in alternating Euler-Ingles and quaternions for x, y, and z. Then the user can go on MATLAB, and here's our script. When the script is run, the program prompts you to input your designated data file. As you can see, it's a text file. And what the program does is it locates what's called a period of significance, which is basically when the dancer's leg should be at 90 degrees. It does this by using, it has predetermined timestamp ratios because although the dancer may be performing the dance faster than a previous trial, the ratios are still generally the same. It also calculates the slope. Of the region of significance and the average. And the reason it calculates the slope is because it needs to compensate for possible skewed data. And the program returns whether you're above or below the accepted value. And in our case, we put the margin of error at 10 degrees. And it also plots your current data file alongside a predetermined ideal data file. You should be able to see it. So it's prompts for data file. Like really lagging. But that was our plot. The red data is the current data and the blue data is the ideal data.
Our original goals were to create a three-dimensional animation that uses the data so the user could visualize better the movement of the leg, and also we wanted to make a computer code that would help dancers perfect their technique. Due to time constraints, we were unable to create the 3D animation, but we were still able to visualize the Euler-Ingles using a MATLAB program, as you saw before, and we were successful in creating a code that would help dancers perfect their technique. There are many improvements that could be made or future possibilities. We could add real-time feedback so the dancer knows when a mistake is made as it's being made instead of afterwards. We could also expand the library to include more dance moves or monitor more parts of the body. We could vary the error, which right now is about plus or minus 10 degrees, so we can have different levels of difficulty. We can add a camera connection so that a picture is taken when a mistake is made. And finally, this can be applied to areas beyond dance, such as physical therapy or personal training.
Finally, this project would not have been possible without the help of our mentors, Dr. Sylvia Kokal-Filipovic and Dr. Predrag Spasojevic. We'd also like to thank the graduate student, Karim Bana, for helping us set up the program and also help set up the sensors with us. We'd also like to thank the entire Governor School of Engineering and Technology staff, especially Director Eileen Rosen, Assistant Director Jean-Patrick Antoine, and finally our wonderful residential teaching associate, Elise Trivette, for helping us throughout the past 4 weeks in creating and completing this project. And finally, we'd also like to thank the sponsors of GSET who generously donated funding in order for us to come here and do this project. Thank you. Any questions?
give it time. This is your only chance. No one? Alright, if we don't have any questions, we're gonna move on to the next group.